Good day, students. On behalf of the Department of the Electrical and Computer Engineering, we welcome you all to this session regarding combinational logic design for the course Digital Logic Design. So let us see the contents in which we will going to discuss in this class. First of all, we will be having the review of the previous class, what we have learned in our previous session. Then we'll move to the examples of the binary multipliers that has the capability to multiply two binary numbers. Then after discussing binary multipliers, we'll switch to the magnitude comparators that have the capability to compare two numbers in terms of equality, in terms of greater than, and in terms of less than operations. After discussing magnitude comparators and implementing them, we'll switch to the decoder circuits. What are the decoder circuits? How they function? And what are their applications? We'll discuss some of the basic examples regarding decoder circuit design at the end of the class. So today's discussion is also from chapter number 4, that is from the book Digital Design with Introduction to Verilog HDL, and we will be discussing the content from page 168 till page 175 of chapter number 4, the 5th edition. Now coming to the binary multiplier circuit, first of all, that circuit has the capability to multiply two binary numbers. We'll discuss our example of the binary multiplier circuit that has the capability to multiply two binary numbers of 2 bits each. So the basic principle of multiplication is same as we used to perform multiplication with the decimal numbers. So here, if you see in this example, A and B are the two numbers with respected binary bits. B0 and B1 are the binary bits for the number B, and A0 and A1 are the binary bits for the number A. B0 and B1 are collectively known to be the multiplicand, and A0 and A1 are collectively known to be the multiplier factor. So how we're going to perform the multiplication? The same principle which used to follow for the decimal numbers, we have to apply the same principle on the binary data as well. First of all, the A0 is bitwise multiplied with B0 and B1 in order to produce the product terms. So when A0 is multiplied with B0, the first term is known to be the A0 and B0. Then A0 is multiplied with the higher term of the B number, that is B1. So A0 is being multiplied with B1. So the product term is A0 B1. Now the point which I have to mention is that the first product operation that we have achieved by multiplying A0 with B0 and B1, this is known to be the first partial product. Then we'll place to the next placement. For the next multiplication, we'll move one placement further and we multiplied A1 with B0. This is the product term of A1 B0, and then A1 with B1. Now if we see the number of product terms in our result, we've got C0, that is the first product term. Then C1 is the addition of A0 B1 and A1 B0, and similarly C2 is A1 B1, and if some carry is been produced from the previous addition, that has been added with that. And the C3 term that is not shown in this case is if, for example, A1 and B1 are is also 1 and the previous carry is 1, then the final carry is also produced. One thing that has to be noticed in this multiplication process is that the number A has the total number of binary bits that are equal to 2, and B has also 2 binary bits, but the product has the binary bits that are basically the 4 binary bits. So the resultant would always be equal to the binary bits of A added with binary bits of B if both have the same size. So multiplying the two-bit numbers, the result will always be of 4 bits. Let us see an example of a multiplication in this case, and then we'll try run this example on our given circuit. For example, we've got B1 equals to 1, B0 always is also equals to 1, A1 is 1 and A0 is 1. And if you multiply these two numbers, so first of all this 1 is multiplied with this whole number, then for the next partial product, this one is multiplied with this number. So the first partial product is 1 multiplied with 1 equals 1, then 1 multiplied with 1 equals 1. Then we'll shift the higher replacement for the next multiplication. 1 multiplied with 1 equals to 1, and 1 multiplied with 1 equals to 1. And then we're going to add these partial products together. So the first result is 1. 1 plus 1 equals 0 with 1 carry. 1 plus 1 equals 0 with 1 carry, and that is the final result. So 3 multiplied by 3 equals 9. So we got the binary value of 9 at our result. Now we're going to try run this example on our circuit. The terms in our partial products are being represented by the AND operation. If you see this expression carefully, the A naught AND with B naught and A naught AND with B1. Similarly, for the second partial product, A1 AND with B naught and A1 AND with B1. So the product terms are being represented by the AND operation. So the first product terms of the first partial product is being represented by these operation, and the second partial product is being represented by these two AND gates, and these bits are added with the help of half adder circuits. So the first multiplication is A naught with B1, so this is C naught, that is the first term. And then the second multiplication in the first partial product is A naught multiplied with B1, so that is the second term in the first partial product. That term is being added with A1 B naught, that is being generated by this AND gate. And similarly, A1 B1 is being added with the previous carry. In any case, if there is a carry produced in our previous edition, then that carry has been added, and the product terms are C0, C1, C2 and C3. So A0 was 1, A1 was 1, B0 was 1, B1 was 1. So the first product term, that is C0, is equal to 1. So this 1 and 1 equals 1. So 1 plus 1 equals 0. The sum result is 0, and the carry is propagated or forwarded for the next addition, that is this one. So 1 plus 1 equals to 0 with final carry. The number of AND gates basically are dependent upon the number of product terms that are appearing in our partial product terms. So let's discuss uh, a bit complicated example rather than this simplified example to explain the concept of binary multipliers, in which we are going to multiply the two numbers. One is of 4 bits and the other number, the multiplier, is of 3 bits. So for example, we have to multiply 1 0 1 1 with 1 0 1. So if you perform the if you perform the multiplication operation, first of all, this bit is multiplied with the whole number, then 0 is multiplied with the whole number, and 1 is multiplied with the whole number. We will be getting 3 partial products, and we're going to add these partial products together. So 1 multiplied with this number will give us 1 1 0 1. This is the first partial product. The second partial product is 0 0 0 0, and the third partial product is 1 1 0 and 1. So we're going to add these partial products together at the same bit placement. The first addition result yields 1, the second 1 plus 0 yields 1, third 1 plus 0 plus 0 yields 1, the fourth 1 plus 0 plus 1 yields 0 with 1 carry. So 0 plus 0 plus 1 yields 1 and 1. So that should be our product result. So if you see the number of bits in our result, that is the first number was the 4 bits and the second number was of 3 bits. The resultant should be of 7 bits. So in this case we are getting 6 bits, but we have those scenarios in which the 7 bits can be produced. For example, the carry that is generated in this placement in some particular scenario will produce the 7th bit in that scenario. So let us see the circuit, how that stuff is being implemented. So if you see the diagram here, we've got 12 AND gates. Since in our previous slide we've discussed that the product terms are being represented by the AND operation, and we've got 3 partial products. So the first two partial products are added with the first 4-bit adder, and the final partial product, the resultant of that summation, is been added to the third partial product in order to produce our final result. So if we see the 4-bit adder circuit, the first adder circuit, if we observe that adder circuit carefully, then A0, A1 and A2 that are being applied at the AND gates together, and B0, B1 and B2, basically these lines are connected with each other. So in order to avoid complexity, these interconnections are not shown. So the first partial product is the A0 multiplied with B0, B1, B2 and B3. The second partial product is A1 multiplied by B0, B1, B2 and B3, and the resultant two partial products are then added. The first multiplication result is A0 B1 that we have achieved directly. As far as the second and third are concerned, the second partial product is the multiplication result of A0 B1 added with A1 B0. So that is our second product term, and similarly for the third and fourth product terms, and if there is any carry produced in that addition, that should also be used for the addition for the next partial product. The third partial product is achieved by these sort of multiplications, and then the resultant of the addition of the first two partial products, the respective terms, are being added with the third partial product in order to give the remaining multiplication bits. Now let us switch to the magnitude comparator. Magnitude comparator is a circuit, basically it's a comparator circuit. So the comparator circuit, as far as its name is concerned, has the capability to compare something, to compare two numbers. So the magnitude comparator circuit is basically a circuit that is used to compare the magnitude of the two numbers, and as far as the magnitude of the two numbers are concerned, either the numbers have the same magnitude or the numbers have different magnitudes. So in case of the same magnitudes, we can say that the both numbers are equal, but in case of the different magnitudes, one number can be greater and another number can be least, so and vice versa. So in this particular scenario, we will be implementing the three possible cases. One for the equality, when both numbers are equal, the circuit should be capable enough to detect the equality. If both numbers are equal, it should indicate the equality. If the first number is greater than second number, and it should also indicate that, and vice versa. So basically we've got two inputs for this comparator circuit. A and B are the inputs, both are of 4 bits each, and we've got three distinct outputs, one to represent equality, one to represent greater than, and one to represent less than. If you see the block diagram of this particular scenario, then we've got a circuit, a comparator circuit, that has two numbers applied at its input. The first number is A and B of 4 bits each. This is basically a comparator circuit. MP, I'm writing in a short form, and has three output lines. One for equality, one for greater than, and one for less than operation. If both numbers a and b have the equal magnitude, then this output line should go to high and the remaining two output lines should remain at 0. If a is greater than b, then this line should go high. These two lines should be at 0 level. And if b is greater than a, or in other words a is less than b, then this line goes to high and both the other two outputs should be at 0. The similar kind of concept can be implemented by using the programming languages. If you have experience of C, C++, then we can clearly see that the comparison operation or the relational operation can be implemented by using the conditional structure. So if that sort of case is implemented by using some programming platform, then it can simply be described by this algorithm that if A is equal to B, then EQ should be high, GT should be low, and less than should also be low. The next condition will be else if because this structure will continue unless and until all the conditions are covered. Else if A is greater than B, then in that case EQ should be 0, GT should go on 1, and less than LT should also be equal to 0. And for the final else, if A is less than B, then in that case LT should be 1 and other two outputs should be 0. As far as the design approach is concerned, we've got the total number of entries that are equivalent to 2 raised to power 2 into 2n. So that are really huge and large entries when we've got a large number of n. So we can use the inherent regularity of this problem to reduce the design effort and to reduce human errors. And we can see how we're gonna reduce our circuit, and we can use inherent regularity of the problem in order to reduce our design effort in our next slide. So as far as the algorithm is concerned, we can see that we've got two numbers of 4 bits each. This is A0, A1, A2 and A3 for to represent A. Similarly, B0, B1, B2 and B3 represents B. A equals to B if all the bits at the same placement are equal, then we can say that A is equal to B. That means if A3 is equal to B3, A2 is equal to B2, A1 is equal to B1 and A0 is equal to B0, then we can say that A is equal to B. If we see the implementation of this equality condition, then we can see that a particular logic gate that can be used to test the equality. If we observe the behavior of the exclusive or the exclusive NOR gate, then we can say that we can easily implement the equality condition by use of the exclusive or exclusive NOR gate. So if we can say that equality, in order to check the equality the bits xi basically represents the equality bits at that particular placement, that is equivalent to ai into bi or ai prime into bi prime. That is basically the term for the exclusive NOR operation. So we also know that exclusive NOR produces 1 if both the inputs are equal. So if x3, the product of x3, x2 and x1 and x0 is high or equals to 1, then we can say that A is equal to B. Similar is the case with A is greater than B. So first of all, we start our comparison from the most significant side of the number. So if the most significant side of the number is inconclusive, then we'll switch to the next lower placement in order to compare our numbers. So first of all, we'll compare A3 with B3. So A3 is being compared with B3 prime, and then uh, if this result is inconclusive, then we'll switch to the next placement, and in the next placement we'll move in that scenario if both the numbers are equal. So x3 is the case if a3 was equal to b3, then we'll move to the next placement, that is a2 and b2. So x3 is being ANDed with a2 and b2 prime and similarly if this also results inconclusive, then we'll switch to the next lower placement, and we only switch to the next lower placement in that case if uh, the upper bits or the most significant bits are in the comparison are equal or same or inconclusive. So this is the term or the expression that is used for a greater than b, and similarly for the a less than b, this is basically, this is condition is for a less than b. Let me correct this. This is a less than b. For the a less than b, we've got this expression. As far as the implementation is concerned, I've clearly mentioned that due to some irregularities in the circuit, we can clearly say that we have a frequent use of the comparisons of in terms of the exclusive OR operation, that is x3, x2, x1 and x0. So in terms of implementation, we can either implement by using the exclusive NOR gates or the exclusive OR gates. Since most of the terms are common in the complete circuit, then instead of implementing them separately, we can utilize those regular terms in order to avoid complexity. So this is the logic diagram for magnitude comparator circuit that is used for equality, greater than and less than operation. So those terms which we have obtained in our previous expression are being implemented here. Now let's move to the decoder circuit. So decoder basically, as far as its name is concerned, decoder is going to decode or going to extract some information from the coded information and going to convert it into all the possible combinations. So basically we are extracting information from the coded sequence. So a code is being applied to the input of the circuit, and that circuit has the capability to decode that particular code into all the possible combinations that can exist in that code. So n to m decoder, how we're going to read that? It's n to m line decoder, where n is the number of inputs and m are the number of outputs. If n is a binary code that has n bits, then we have 2 raised to power n distinct information bits that are available in a code. So we've got 2 raised to power n output lines basically. So m is basically equals to 2 raised to power n output lines. So if we see in terms of the block diagram here, then we've got a decoder circuit that has the n number of lines at its input and got m number of lines at its output, where m is equal to 2 raised to power n. So how we're going to read this decoder? We can say that it's n to m line decoder. So decoder is a circuit that has the capability to decode the coded information and convert it into all the possible combinations. And the one important thing is that only one output can be active high at any time. So in this particular setup where the truth table of 3 to 8 line decoder is being shown, which shows that we've got a 3-bit code that is being applied to the decoder input and the 8 lines that are dedicated for the output. We can see a particular classic example of decoder when we were using the code conversions. If you remember that we were converting the binary to octal. So in that particular binary to octal conversion, we've got a binary code of 3 bits and we've got 8 distinct octal combinations or octal digits in order to represent some particular binary codes. So for each particular binary code, we've got a one distinct octal digit in order to represent their relationship. So we can easily say that that conversion can be performed by using 3 to 8 line decoder. So if you see that we've got inputs X, Y, and Z of this setup, and the outputs are D0, D1, D2, D3, D4 till D7. So if we can consider the particular example of that binary to octal conversion, these D0 till D7 are basically the octal digits. D0 represents the octal digit 0, D1 represents the octal digit 1, and similarly D7 represents the octal digit 7. So in any particular case, if we've got the output D4 equals to 1, that means in that particular case, we have applied the binary code of 100. So this is the decoding process that basically maps the particular code to the unique distinct lines in order to convert that coded information into all the possible combinations of the coded information. One important thing which can be observed in this discussion is that by default all the outputs of the decoder are set to 0 and if in order to show the change in the output, one decoder line is particularly gonna switch its level from 0 to 1 in order to represent that particular code. So when we applied the code 000, this code, the D0 line is high in order to show that 000 was applied at input. So if we see the implementation, we can clearly say that from the truth table, when we extract the min terms, we can say that each output line represents a one min term. And so D0 is equivalent to X prime, Y prime, and Z prime. D1 equals to X prime, Y prime into Z. And similarly, D7 equals X into Y into Z. So number of AND gates which are used in this circuit are basically 8, since we've got 8 min terms. We've got the code of 3 inputs, so the total number of combinations that are 2 raised to power 3 equals 8. So this circuit now has the capability to convert uh, the binary code of 3 bits into the octal codes in this particular example, where D0, D1, D2 till D7 represents octal digits that can be implemented by using 3 to 8 line decoder. One of the most important functionality of the decoder is that we can implement any combinational logic circuit by using the decoders and OR gate only. Since we know that each decoder term, the output term is representing a main term, then we can easily use those main terms in order to implement our basic combinational logic module. So this is also an option. If you've got the decoder circuits available, then we can utilize those decoder circuits in order to implement some Boolean functions as well. Let us see the example of the full adder circuit that is being implemented by using 3 to 8 line decoder. So this expression for the sum is equivalent to that is basically the sum of minterms, that is the minterm number 1, 2, 4, and 7, and the carry output is being represented by minterm number 3, 5, 6, and 7. Since we know that when we applied the code of 3 bits, the output is being converted into 8 distinct lines. So in that particular case, we can say that we simply have to OR those particular terms in order to produce sum and carry output. So for the sum output, if we see the sum output, these are the OR operation between 1, 2, 4, and 7. Similarly for the carry operation as well. So we can implement uh, the Boolean functions very easily by using the decoders and OR gates only. So that is also one option to implement any sort of Boolean functions. We can implement Boolean functions by using the combinational or the primary gates. We can implement those Boolean functions by use of the universal gates as well. We can implement those Boolean functions by decoders. Also, we can implement those Boolean functions by multiplexers. Also, we will gonna see the multiplexers in our coming classes. How we're gonna implement the multiplexers by using multiplexers. We can implement any sort of combinational logic function. So we've got variety of options available in order to implement combinational logic design. We're gonna switch to the next concept, that is decoder with enable input. So we've seen sometimes in our digital circuit, we've got some dedicated lines that provide us the control over the device in terms of enabling the device or the disabling the device. So we've got some dedicated lines that their status represents the enabling and disabling process of that particular device. So when the device is disabled, the device is producing the output that is on the default level, and when we enable the device, then the output are being reflected with the change in the input. So if you see this particular circuit and this particular table, where we got a decoder that is a 2 to 4 line decoder basically, with an enable input that is being represented with E, where A and B are basically the inputs, and D naught, D1, D2 and D3 and so on and so forth are basically our outputs. So D1, D naught, D1, D2 and D3. This is for the first case. So this enable is basically the active low enable circuit. If you see that the circuit is in its normal mode of operation when enable is set to 0, and when enable is set to 1, the circuit is in its default state, that is all the outputs are switched to logic 1, because we are using NAND gates, and this is active low output decoder with active low enable circuit. So when this enable is switched to 1, this inversion process makes it 0, and whatsoever the inputs of A and B are, the outputs are switched to 1, 1, 1, 1. The outputs are not affected with the change in input. But when we switch this enable to 0, this inversion makes it 1. Now the change in input is reflected at the output. When the inputs are 0, 0, D naught will be 0, and rest of the outputs are switched to 1, and similarly for the rest of the cases as well. So this enable inputs basically enables us, uh, gives us more control on our circuit in order, in a way that we can enable or disable a circuit. Either the circuit can be enabled, then the circuit will be operating in its normal mode of operation, and if the circuit is disabled, then all the outputs are being held to the default level, so the change in input is not reflected at the output. As far as the block diagrams are concerned, the decoders can be represented by it's a 2 to 4 line decoder, the previous example which we have discussed. Active low enable, so we have got bubble or inversion at the enable line. A, B are the inputs, and D naught and D3 are D1, D2, D3 are the outputs. With these bubbles indicate that these outputs are active low outputs. Their default value is 1, and their value is switched from 1 to 0 when the output level is changed. We can clearly see that the demultiplexer circuits are implemented with the use of decoder circuits. Demultiplexer circuits are basically the data distributor circuits that are basically the decoder circuits. So the select lines that are that are responsible to distribute the data are A and B, these two lines, and this E is basically the enable or the data or the input is applied here, and according to these select line, these inputs are being distributed among D naught till D3. We will gonna discuss these demultiplexers in detail when we will be discussing the multiplexer circuits in our coming sessions. The one important thing which we have discussed previously in our previous classes is that the effective use of resources sometimes matters a lot. So we can implement some combinational logic modules by using the existing combinational logic modules. For example, we can implement 4 to 16 line decoder by using the 3 to 8 line decoders. if we have got 3 to 8 line decoders available, then it's better to use those decoders in order to implement a 4 to 16 line decoder. So if you see the combinations that are being presented to the 4 to 16 line decoders, we've got the number of inputs that are 4. So the total number of combinations that are being represented at the output are the 16. So those 4 lines are being converted to those 16 lines depending upon the conversion mechanism. So here we can see that W, X, Y, Z are the inputs. Uh, Let me draw a block diagram of that particular decoder. W, X, Y, and Z. This is W, X, Y, and Z, where W is being considered as the most significant bit and Z is being considered as the least significant bit. And we've got the number of outputs that are being represented as D0 till D15. So this is basically 4 to 16 line decoder. 4 to 16 decoder. So if we see the truth table, if we draw the truth table of 4 to 16 line decoder, we can see that for the least significant 8 combinations from D0 till D7, the most significant bit W, this bit, is 0, and for the remaining 8 combinations, the most significant bit W is equal to 1. So this is the driving factor that is going to enable or disable these decoder circuits. When the W bit is 0, the first decoder should be enabled and the second decoder should be disabled, and XYZ that are being commonly applied to the both decoders. So whatsoever the X, Y, and Z status is, that is being converted to D0 to D7 or D8 to D15 depending upon the value of W. If W is 0, then this decoder goes to disable state because it's active high enable decoder, and this decoder goes to enable state. So 0 is being converted to 1, 0 has been converted to 1. So this is enabled and this is disabled. So the 3-bit code is being reflected on D0 to D7, and if we switch the value of W to 1, then this decoder is disabled, this is enabled. Now this 3-bit code is being reflected at D8 to D15. So we can implement a 4 to 16 line decoder by using 3 to 8 line decoders as well. Well, student, this is all for the class. I hope so you will be able to understand the decoder circuits as well as the remaining topics which we have discussed in our class. Let us have a quick revision which we have studied in this class. We've discussed some variety of circuits, including the comparator circuits, in order to compare the numbers that has the capability to compare two binary numbers, as well as the decoder circuits. We've discussed that decoder circuits are the circuits that has the capability to decode some coded information into all the possible combinations of levels that are being mapped to that particular code. And to start with the class, we've discussed a multiplier circuit and we've discussed examples of the multipliers. So the multiplier circuit is a circuit that has the capability to multiply two numbers. So the size of the two numbers can be same, can differ. The resultant product size is always equal to the number of bits added with the of the multiplicand added with the number of bits with the multiplier. So if we've got a number of, let's assume the multiplicand of is of 8 bits and the multiplier is of 4 bits, then the resultant product will be 8 plus 4 equals 12 bits. So I hope so these topics are now clear. So for the question and answer session, your questions will be welcomed in our question and answer sessions. In our next class, we will be switching to multiplexers and demultiplexers, and also the encoder circuits, and that are the reverse of the decoder circuits.